So we'll just start at the top here. So the simplest thing you can do is just memorize everything that everyone ever showed you.
Voronoi should have another O.
Oh, between N and I?
Yeah.
Oh, I'm sorry. Thank you. Matt, can you write that down and beat me up later? Thanks, Frank. So what in America, we're brought up to disparage rote learning. Right? It's like, we're all individuals. I'm going to do my own generalization, and it's all about the process, not actually knowing anything. And stuff like that. And people from Singapore and Japan who routinely beat us on all those standardized tests, like to laugh. But nearest neighbor learning has a few good things to say about it. It has bad things too. What are some advantages and disadvantages of K nearest neighbor as a learning algorithm?
I guess it takes a lot of memory, probably.
Yeah, if you have a lot of training examples, exactly. Yeah, you have to remember everything, so that's a pain. I'm pretty bad at remembering stuff. So, yeah.
Do you remember every single chair you've ever seen?
Hell no. No, I did see this beautiful chair once. I remember, and I've never been able to find it again. It was sad. Well, I was in the market for chairs at the time. I got a real job out in the world, and they pay you real money, and you can actually buy stuff. So I was like, wow, I'm going to get some nice chairs. Like all the chairs I had, the seats were all like you could fall through them and stuff. I was like, oh, I'm tired of being a grad student. I'm going to get real furniture. And I saw this great chair in the window, and then I moved to New Hampshire, and I've never seen that chair again. And it's the one that got away. But I do remember it vividly. The more we talk about this, the more vividly I'm remembering it. Beautiful chair. So it requires a lot of memory. That's a bad thing. What's a good thing?
It is pretty good at figuring out if something is a chair or not.
Let me modify what you said. It does great on the exam. Right? If somebody gives you the same question that they already told you the answer to, you get 100%. Right? Professors hate that when you say something to the students and then you ask it on the test and they get it all wrong. Because you're like, oh, couldn't you just remember? No, because we're all busy generalizing all the time. In fact, there are these great, speaking of cognitive modeling, there are these great cognitive psychology studies where you say a sentence to somebody and ask them to repeat it, and people get it totally wrong. They get the meaning absolutely perfectly. And so this is taken as an argument that English must not be the language of thought, that you translate what you hear into some mental representation and you remember that, but you don't remember what surface words were necessarily used in the sentence. It's really cool results. So nearest neighbor does great if, for example, maybe you know all the questions that will ever be asked. So if you could line up all the chairs in the world and say, look, here they are. Here they are from all different views. Then you'd never get anything wrong. You have perfect accuracy. It'd be great. So there are some situations where you have a very controlled world and it's not a big problem. Like, if you're making a robot to play chess, right, and you're looking at the chessboard, it's always going to be those however different number of pieces there are, not that many. And it's always going to be lit from above and pretty straightforward. You could actually reasonably memorize a lot of the examples. So that's one of the great things about nearest neighbors. Now, K equals 1 means you look at the very nearest example and you use the label that it had. So for example, if you're trying to tell whether something is a chair or not a chair, and you get a new image in, you look it up, you find the closest image, and if that was supposed to be a chair, then you say chair for the new one. Now, if you set K equal to 1, it's a little brittle, right? What if there's a little noise in your data? Like you had some undergrad labeling the images, or you did it on Mechanical Turk on Amazon, and someone was supposed to say, yes, it has a chair, no, it doesn't have a chair, but there's going to be a little noise in the process. So if you have K equals 1, it's not very noise tolerant because you take this single closest example and you use that label. So one thing that's fun to do is to turn K up a little bit, and now you take the 3 closest examples and you take the majority. So if 2 out of the 3 say, yeah, it's a chair, and one of them says, no, that's not a chair, then you say, okay, this is a chair. Looks like a chair to me. You have more robustness. So turning K up past 1 can be a good thing. You have sort of like a majority rules among the examples that are closest. There is this awful thing, though, that to use K nearest neighbors, you have to define what a near neighbor is. And this is both a curse and a blessing. It's a blessing, if we want to be optimistic, because you can do whatever the hell you want. You don't have to use Euclidean distance. If your feature space or the dimensionality of the instances you get in, if they have all kinds of different things, like if it's cars, where you've got, you might be comparing cars on their color, their size, their engine displacement, whether they have anti-lock brakes, whether they have a built-in navigation system. I hear they have cars now that have like 2 sunroofs, like even one in the back or something. That sounds like a cool feature. So I'd want to have that in my data set. So you can define your distance function however you want. Maybe I would want to weight the, like, does it have a panoramic sunroof thing, like very highly? And for someone else, it would be like, does it have double chrome exhausts out the back or something? Whatever you favor in your car, you can set your distance function to favor that. So that's a blessing. However, it's also a curse because, of course, it's a pain in the neck to tune the distance function to be whatever you want. Very often, everyone just uses Euclidean distance, and you know what happens then is whatever dimensions happen to be using the largest magnitude units dominates. So if I have like cargo space versus engine displacement, and I do engine displacements in cubic centimeters, and I have trunk space in cubic feet, the engine displacement is probably going to be way larger than the trunk space. And basically, you're going to be finding the car that has the nearest engine displacement and completely disregarding trunk space. Exactly. Ta-da-da! Normalize. One thing you can do is compute the variance and divide through by it so that everything's normalized to like standard deviations of the data. So that's a very common thing to do. It's like you take every dimension of your data set and you normalize it to be mean 0, standard deviation 1. And that way, every dimension has the same input, has the same effect, the same influence on the distance function. So if you use larger k than 1, you're robust to noise. Bad thing, takes a lot of memory. Sparse data in high dimensions, yeah. Whew. People like to do the craziest things. Like, for example, sometimes people give you a short string consisting of a few words called a search query, and they expect you to return like all the web pages that are most relevant to that query. Like, damn them. Like, how do you represent an object in that in an application like that? One common thing to do is called bag of words, where for every possible word, you write down whether or not the document contains the word. So the typical English dictionary has like 120,000 words in it. So now we have a vector of length 120,000 that has a few bits set to 1. And you're supposed to do retrieval on this basis. You're in a high-dimensional space, so it's 120,000 dimensional. It's really hard to get a lot of training data. Even if you're Google and you have 1 billion web pages, it's really hard to get enough to have anybody be nearby. So you'd end up with very flaky classification in that setting, unless you do all kinds of fancy tricks, which of course Google does, but we're not going to talk about yet. So this is called the sparse data problem, and it's a big one, and it's a big deal, especially for k-nearest neighbors, because it's just raw comparison of instances.